what polynomial means. Sum of monomials. Mono. What's mono mean? Mono means one. What it means? Poly literally means many. So there's a mathematical definition of polynomial, which is just going to be complete nonsense to a teenager. So it's best just to give you an example. You've been studying examples of polynomials all of chapter 4. Quadratics. Those are polynomials. Something like 3x squared plus 5x plus 4. Isn't that the sum of many? That's a polynomial.
So,
3x squared plus 4 is a polynomial. For that matter, so is 3x squared. Because there's the hidden 0. Polynomial can actually be one thing. There's always the plus 0 that's under the That makes it polynomial. And there's a mathematical definition I'm not going to go into this. This is completely useless definition. But does the exponent have to be 3? No, it can be 3, 4, 5, whatever.
does it have to be?
There does have to be an exponent, and it does have to be a whole number. That's part of the mathematical definition. But anyways, the goal here is to graph, which is what we'll do at least one example towards the end. But there's a lot of stuff to get up to that point that we talk about. Now, the first thing we talk about is this. That's not in your notes, is it? I cut that out. I just forgot to save it. First thing we need to talk about is that good old funky function notation. It just funks your little heads and you don't know what the fuck to do. Right?
All right.
So we don't.
What the fuck?
Divide that in 3.
I think
Yeah, let x be 3. It's really that simple. But a lot of kids just don't get that. I think they do when they see an easy example, when it starts showing up later, like, I don't know what to do. This means let x be 3. Now, you know, on your homework, I realize you're going to use technology to do it. You better write it out. It's not too much to ask. 2 times 3 to the 4th minus 5 times 3 cubed minus 4 times 3 plus 8. Ain't nobody asking you to figure it out in your head, kids. You know what 3 to the 4th is? No. Just, that answers it. 81. But you've got a calculator. Use it. And use the storage feature. Please use the storage feature. Makes it so much easier. Why is that saying something? No, she wants to talk to me, doesn't she? So I'm going to go back over the storage feature today. I'm going to take a 3 and hit STO. Put it next. The nice thing about the storage feature is, you know, it keeps you from making typos. You don't have to worry about all these parentheses, which adds to it. So the equation was 2x to the 4th. Pay attention, calculator. This calculator raises things up in exponential space. You've got to arrow out. Minus 5x cubed. Minus 4x plus 8. That's F3. 23. That's the y value.
I didn't see what you did. Like I was trying to type there on calculator.
First thing I did here was I hit 3. I hit the store button next to the 4 key, and I hit X. And then I typed in the equation as it was given. I'm not going to sit here and retype the equation. Hit 3, store X. Well, if I wanted to find the next one, what is it, f of -1? Let's do the same thing. On your homework, if I ask you to do this, please write it down. I'm not asking too much. That's the only way I actually have an idea, even if you're copying, it says maybe you know what you're actually doing. Now, the nice thing about using the storage feature is once you've done something the first time, you don't have to retype it the second time. Remember that? All you gotta do is say -1 STOX. You guys, if you've been playing along, have to press second enter twice. I have to do it 3 times because of Garrett. And I'm gonna press second enter until I see the original equation I typed in. The answer's 19. So don't be confused by the function notation. Just do what it says to do. Let x be that number. It's really not hard to do. Now, the next question up here says, find the average rate of change over this interval. This is just in here because you kids stink at average rate of change. It's on your formula quizzes. Average rate of change is just a more elegant way of saying what? Slope. Average rate of change is slope. When you see stuff like this, you're just thinking, oh, slope. Now, what's the formula for slope? It's not y equals mx plus 3. That is slope-intercept form of equation. y2 minus y1. Yes, sir, Austin. All right, over this interval 3 to 5. You might know what that means?
Big positive coordinate.
Parentheses 3 to 5 might be, but it says interval. X from x equals 3 to x equals 5. That's what it means. Those are x values they gave you. If you think about your formula for slope, you have x1 and x2, don't you? That's what it gave you. It gave you a starting x and it gave you a stopping x. What else do you need to use your formula for slope? You need your y's. You have x's. How do you get y's? Plug in. Now, did we not already plug a 3 in? Didn't we? That's the first thing we did? What do we know the y value is? 23. So I have a y1 value of 23. How do I get that y2 value? Why don't y'all go ahead and do that real quick? You just hit 5, store x, second enter, second enter. Takes all the 10 seconds. Anybody come up with anything? There, you sit here and do this. 613 try. Don't take that long. The only reason it would take long is you never did it the first time when I was doing it. Well, here's the formula for slope. What goes up top?
Yeah, 613 minus 23.
I wanted to do it.
Okay, yeah, you can handle the bottom.
5 minus 3.
There's a joke there somewhere. 5 minus 3. 613 minus 20 up top, 5 minus 3 down low. What's 613 minus 20? Sorry, 23, not 20.
5
9
I said it last.
Over 2.
over 2. That reduces down
295.
295. So on average, as you go from x equals 3 to x equals 5, you're gaining 295 units up every time you go over 1.
That's a lot.
It's a steep line if you think about lines. These aren't lines.
So you also
But
say.
you guys still think anything over 10 is a big number.
So it goes up 73.75 every 1. That's for me.
No, it goes up 295 units and over 1. That is the slope. The slope is 295 over 1.
3 to 5.
I know, but on average,
Oh, yeah. I was.
So it's over 1.
Find out over 1. 147.5 every 1.
never heard a kid say that. Thank you for sharing that with me, actually. I mean that, because that explains a couple things. All right, here's the concept of what's called end behavior. End behavior is literally how a graph behaves on the left and the right. There's a longer definition, it's right here. It's all gone. How a function behaves, the values of y, as x approaches very large positive and negative numbers. It's how the graph looks on the left and right hand sides. That's what it is. That's why it's called end behavior. Four things that we have to memorize. The degree up here talks about the exponent. We'll just call it some x to an odd degree. What's an example of some x to an odd degree?
X to the third power.
X cubed, maybe even x to the first. Okay. We'll use x to the first as an example because you guys don't know what x cubed looks like yet. The example is going to be y equals, is it the board? It's the board.
Is that the squiggle? Oh, shit. You gotta go smack it in the thing.
That's why we get so strange. By the way, leading coefficient here is positive.
We'll have to open the big jobs. That's what I say.
Let me use the example y equals x. It's a line. Where's it across the x-axis? Origin. Slope is 1. Y equals x looks like that. You focus on the idea of end behavior. Starts down here, ends up there. Everything with an odd exponent behaves the same way. It starts low on the left and ends high on the right. Everything. X to the fifth looks the same. It's just sequence. They all look like that. They all start low and end high. But now here's the reading. The reading of this, mathematical reading for some kids is kind of hard to understand. If we move to the right, what x value are we approaching if we do it for all of our life? Positive infinity. So as we move to the right, x approaches infinity. F of x is fancy for what? Y. What happens to the y values? They also rise further than infinity. Now as we move to the left,
It goes to negative infinity.
x approaches negative infinity. Y falls further than it.
Why is the arrow just going the same direction?
Where's what?
The arrows?
The arrows are the end behavior.
They're going the same direction. How do we tell whether it's a negative or positive? Based off reading that.
Yeah, because like,
Okay, what's your question?
well, how are you supposed to know where to put which if the arrows, if they look the exact same, the question?
It doesn't matter if you start at the top off with x as x approaches negative infinity. Are you talking about what I'm writing here at the end?
I'm talking about the actual question, like.
How do you tell if it's a positive infinity or a negative?
How do you tell if it's going left or right? I was just asking left or right. If the arrow's
Because the
going the
arrows
same
are
way.
in the exact same direction.
Like all going towards the right.
You think the arrow has anything to do with it? No, I'm sorry. This arrow, when you see an arrow like that in this form, it reads, this line reads as x approaches. As x approaches infinity. What happens to y?
So if the line was flipped the other way, it'd be a.
No. I just got confused.
That's what the arrow is telling you as you approach. That's how I've been reading it. Anyways, okay, so that confusion's gone. It's a new one. We're still going to deal with an x to the odd here, but we're going to make the leading coefficient negative. But still x to the odd. Leading coefficient is negative. Now, if we took our example, we made it y equals negative x. Look just like that one, but with a negative slope. Start high and low. All we care about right now is studying what's called end behavior. Well, that thing starts its day high, runs out of drugs, and ends low. What happens?
That's the question.
Let's go ahead and work with as we go right. As we go right on this graph, that's when x approaches what? Positive infinity. What What happens to the value of y? It's negative. So we talked about what happens on the right, now we talk about what happens on the left. As x runs left to negative infinity, what happens to y? Goes to infinity. That's end behavior for any polynomial that starts off with an odd number as an exponent. Two more, and then we actually get to analyze one. All right, so here's these. We just did x to the odd. What do you think we're about to do here?
That's even.
X to the even. This will be x to the even. What's an example of x to the even? X squared is a perfect one. That's the one I'm going to use because you are supposed to have an idea of what x squared looks like. I hope you do. We'll use x squared as an example. What does it look like? Looks like a u. It's just some other function x squared. Where does it cross the x and y axis? The origin. That's what it looks like. How's it start its day? High. How's it end its day? High. Just the word it sucks. The end behavior looks like this.
So it starts high, dips, and then inside.
Something happens in here. So as x moves to the right, so does y. Y goes up. As x moves to the left, it still happens to y. It goes up. Oh, by the way, that was positive. Still x to the even. Leading coefficient is negative. Same example, but a negative x squared, which is still a parabola, but this time it opens how? Down. All we care about is what happens at the ends. The ends are both those.
So maybe negative. That's always going to be infinity and then negative.
Oh yeah, always. These aren't even legit questions. These are just describing things. But as x moves right on this one, what happens to y? Decreases. Falls to negative infinity. As x moves left, what happens to y? Decreases to negative infinity. That's the concepts of end behavior. This whole section is about studying polynomials. You learn how to graph them, find all their zeros. A lot of interesting stuff in it if you like math. If you don't, become an Amish. Well, when you figure out the middle stuff, I'm making tables. The middle stuff's what's interesting. The end's not. All right, determine what you know about the degree and leading coefficient of the polynomial shown below. Just focus on end behavior. That's what you know so far. How does example A start its day? Low. How's it finish? Now look at the notes you just took. What starts low and ends high? And x to the odd. Is it a positive x to the odd or a negative x to the odd? It is a positive x to the odd. Example B. How does it start its day? How's it end its day? What starts and ends low? Even. Anything else about that even?
It's negative.
It's negative. First one is a graph of probably x cubed. The second one's probably x to the fourth. Some variation of it. Notice the text here, what it says. Leading coefficient.
It's not, you know if it's even. Is it like that?
X to the even. Starts low, ends low, if it's negative. Evens are always the same. They're either both up or both down. Odds are different, which seems appropriate because odds are different. Aren't they? Aren't odd people different? What was I trying to put there? Oh yeah, I underlined something. That one said leading coefficient. the thing that starts it off determines end behavior. End behavior is determined by negative x cubed because it's the highest degree that you see. Not necessarily because it starts it off. I mean, we could rewrite things in the wrong order. But the highest degree you see is negative x cubed. That determines your end behavior. And you've got 4 little graphs you can look at. Negative x cubed, how's it start its day? High. Negative x cubed starts high. Negative x cubed looks like this. Starts high, ends low. You can go back and look at your notes. Check it. Let's say x to the odd, negative x to the odd. Negative x to the odd starts high, finishes low. Promise you it does. Probably on the previous page. You're probably not going to look. But I know this. I know that no matter what happens in the middle, this graph is going to shoot up to positive infinity there. At some point in time on the right, shoot down to negative infinity. It's the stuff in the middle that I care about. I already know what the ends look like. I just need to figure out what the middle looks like. So you do this by making table fits. That's really all you do. But yeah, I don't want you doing white. Don't want you doing white. You're not learning anything when you do white. I know you think it's stupid. I know you do. Make a table centered around 0. Go back a couple of units. Go forward a couple of units. GI84s are wonderful, but they don't give your brain time to establish patterns and figure things out for itself. It doesn't something to do everything for you. You guys will be a robot.
Ooh, about that -0.
Maybe you should let GI84 do anything for you. Anyways, I'm going to do 2 of these with you so that I can walk you through it, and then you guys can figure out the rest of it. I'm going to take a 0. I'm going to store it to x. You probably should too. I'm going to type in the original function. Negative x cubed, not minus x cubed, negative x cubed. There's a difference. Don't need them when you're doing it this way. One of the things the storage feature saves you on, you don't have to worry about parentheses. That is a -3, not a -3. You have to use the -3. So 0 returns -3. Now, the nice thing about storage feature, again, I've been showing you this, but a lot of you guys look around, you don't play along, so you don't know this thing. Say I wanted to figure out what -4 was next. I'd take a -4, I'd store it to x, and I'd press enter. How many times do I do second enter to bring up that equation and pipe back in? Twice. Second enter once brings up what I just did. Second enter again brings up the prior stuff. There I can press enter. 65. I want you guys at random to pick one of them and figure out what it is. So in 30 seconds we have all our numbers. Somebody just pick something and do it. Just pick something and do it. Oh man, you're still writing the table down. Y'all gotta learn. In Mr. Milbrath's room, we don't work at the slowest pace. We work at my pace. That's the way it is. Actually, we only work at about a third of my pace. You're in math genius. I'm a math genius, so I'm just kidding. We gotta have some numbers right now. Darren, you got anything figured out? Give me one. 2 is what? -1. Austin, what you got?
I got 3 -12.
Anybody else got what you got, Paul?
I got 4 -71.
4 at -71? I don't think, is 4 -71?
And -1 is a -4.
-1 is where?
-1's a -4.
Yeah, I got -3 now.
It should go 65, 24, 3, -4, -3.
Anyways, I'm still missing -3 and -2.
One is -4.
One is -4.
-3 is 24. And the -2 is 3.
The only ones we can actually plot are those, right? That's it. Back 2, rise 3. Back 1, fall 4. 0, -3. 1, -4. 3, -12. I'm actually going to put that on here, just down here. And let's see, what was -4? -3 was 24. Isn't that like up here somewhere? Is that expected? Was this expected to be off the grid?
No.
Look at the end behavior.
Yeah.
It was expected, wasn't it? Was this expected to be off the grid? Look at your end behavior. That was an expected outcome. Sooner or later, we knew that this thing would fly off our grid. Because we knew the end behavior. Now, when you actually connect the dots here, like, your line can't be crossing itself. And these things have curvature. These are polynomials. They're not straight lines. But you come in from up high, you drop down, come up, pass through nicely. It's a smooth curve, kids. Won't cross paths. You just work from left to right. You got your homework. I think.
Yeah.
Go away.
Don't come back.
I'll come back tomorrow.
Good.